kids, remember Buzz Lightyear from Toy Story? Remember when he first met Woody and used his laser? Well, that laser was just a toy. But at NASA Langley Research Center in Hampton, Virginia, they use real lasers. You see, the lasers that are used at NASA study the Earth's atmosphere. In today's episode of NASA Connect, Van and I will take you to NASA Langley Research Center, where you'll meet scientists and researchers who use lasers and satellites to measure particles in the Earth's atmosphere. So stick around as NASA Connect takes you on a trip to the upper reaches of the Earth's atmosphere. And remember, guys, it's mathematics, science, and technology that make it all possible. Hang on as NASA Connect takes you to infinity and beyond the Earth's atmosphere.
By the looks of it, your engine's in need of a serious tune-up. You need to replace your catalytic converter. Your van's sick, and it needs help. And you, young man, are contributing to global pollution.
So, what does that mean?
It means you're rejected.
Is there anything else?
No thanks.
Hey, stranger. Why the long face?
Hey. Mr. Murphy rejected my van. He said that the particle emissions coming out of my van were too high and that I'm polluting the air.
You're upset, huh?
How does he even know my van's a polluter? So the van smokes a little. Big deal. I mean, how much can a little smoke damage do to the air? After all, it's only one van.
Well, it is hard to understand how they measure what's in the smoke coming out of your van, because a lot of it we can't see. That's why garages that inspect vehicles have special tools to measure the amount of particle emissions in a car's exhaust. So you see, Van, if your van's emission levels are too high, you get the big rejection.
Well, how can you measure something you can't even see?
Okay. Just because you can't see something doesn't mean it's not there, right? Take the air, for example. There are particles in the air right now that are so small, even our eyes can't see them. Believe me, those particles are there. Check it out. In the weather section of the newspaper, they report on something every day called the air quality index level. This level tells us the amount of particles or aerosols in the air around us.
Aerosols? Like hairspray?
Yeah, simply put, an aerosol is a particle, either liquid or solid, that is suspended in the air. So yes, hairspray is considered an aerosol.
What are some other examples of aerosols?
Chalk becomes an aerosol after you bang two erasers together. The flakes released into the air when you scratch your body become aerosols. Of course, the dust from desert storms and volcanic ash are also aerosols.
Okay, so there are aerosols all around us, but we can't see them. But I'm still confused. How can we actually measure an aerosol?
Look, why don't we take a road trip to Hampton, Virginia, and visit NASA Langley Research Center and Hampton University. I know some atmospheric scientists there who can help us both better understand how they measure aerosols in the atmosphere. Thank you. You're paying this. We always take my car. Hi guys, welcome to this episode of NASA Connect. I'm Jennifer Pulley.
And I'm Van Hughes. Speaking about measuring aerosols, on today's show, NASA Connect travels to St. Stephen's Indian School on the Wind River Reservation in Wyoming. Students there will show you how to collect aerosols. You can conduct this experiment at your own school or even at home.
And to help you understand the information in our show, every time our friend Norbert appears with a cue card, that's your cue to think about answers to the questions he gives you. Got it? You'll also meet NASA's Educational Technology Program Manager, Dr. Shelley Canright, who will introduce you to some students in California.
Yeah, these kids are hooked up and turned on to our NASA Connect website. You'll see how they're using the internet to learn more about measuring the Earth's atmosphere.
For right now, let's get some expert help and some more background information on aerosols from Dr. M. Patrick McCormick. He's the co-director of Hampton University's Center for Atmospheric Sciences.
How does the amount of aerosols in the atmosphere affect the Earth's weather condition?
The atmosphere consists primarily of oxygen and other gases like nitrogen and water vapor, hydrogen. But did you know that the air we breathe also consists of tiny little particles called aerosols? Aerosols are very important for lots of reasons. For example, aerosols are thought to be important in climate by changing the properties of clouds. If you didn't have an aerosol, it would be very difficult for a cloud droplet to form. In the air, water molecules attach themselves to aerosols, and as they condense, a cloud droplet is formed. The aerosols act as seeds to start the formation of the cloud droplets. In any location, the amount of aerosols in the atmosphere can change how far we can see, the frequency of clouds in the sky, the thickness of clouds, and even the rainfall amount. Some aerosols are naturally occurring in the atmosphere, like sea salt, pollen, and particles produced by volcanic eruptions. Other aerosols are human-made, like factory pollutants, automobile exhaust, and smoke from biomass burning.
Can aerosols affect the temperature here on Earth?
Sure they can. When aerosols like smoke and dust and pollen float in the air becomes hazy. Now, if this haziness reflects sunlight back to space, the effect is going to be a cooling of the atmosphere on Earth. But if this haziness absorbs energy, well, then the net effect is going to be a warming of the atmosphere here on Earth.
After getting tons of information from Dr. McCormick, we drove to NASA Langley in Hampton, Virginia, to talk with Dr. Russell DeYoung, an atmospheric scientist in the Chemistry and Dynamics branch.
Hi, I'm Van.
Hi, glad to meet you. What brings you two here today?
Well, it all started when Van's car failed inspection. It's because his emission levels were too high.
Yeah, I can't believe I got rejected when there's so many other things in the atmosphere to worry about. Can my van's little emissions really affect the huge atmosphere above us?
Okay, good. You've got a lot of good questions, and I think I can get some answers for y'all. Here at NASA Langley in Hampton, Virginia, and NASA Goddard in Greenbelt, Maryland, we study how natural and man-made aerosols affect the atmosphere. You have one vehicle. Every family on your block has at least one vehicle. Your city is full of vehicles. In the U.S. alone, there are millions of vehicles, all burning fossil fuels. Altogether, these vehicles emit huge amounts of particles called aerosols that are carried long distances by the wind. Did you know that in 1991, Mount Pinatubo, a volcano in the Philippines, erupted, releasing massive aerosol concentrations into the air? These aerosols were immediately dispersed into the upper atmosphere. 3 months later, these same aerosols could be found all over the Earth. Okay, your van is a small polluter. But think about this. Think about the combined effect of all the exhaust of all the cars in the world on the Earth's atmosphere.
Wow, that's definitely something to think about. Hey, here's Norbert with some more questions for you to think about.
How do aerosols affect our health?
What is remote sensing?
Name and describe the two types of remote sensing and give examples of each. How are aerosols in the atmosphere measured?
Studying the atmosphere is a fairly new science. In the Chemistry and Dynamics branch of NASA Langley Research Center, atmospheric scientists are trying to determine how many aerosols there are and where they are in the atmosphere. Now, these aerosols are important because they affect our health. Small aerosols can enter our lungs as we breathe polluted air. These aerosols can be deposited deep in our lungs, blocking the lungs' ability to exchange oxygen and carbon dioxide. Over time, this makes it hard to breathe. Here at NASA Langley, we measure aerosols using a technique called remote sensing.
What is remote sensing?
Remote sensing is collecting information about an object without physically touching the object. It's learning without touching. The most familiar kind of remote sensing is the use of our eyes to detect a distant object. We also learn without touching when we hear. For example, when a car beeps its horn, we hear it from a distance and sense we're in danger.
Get out of the street!
You know, there are two types of remote sensing, active and passive.
An early example of passive remote sensing involved the use of a camera. In 1858, the first aerial photograph of land was taken from a balloon floating over Paris, France. This is called passive because the camera uses only the light from the sun to record the image on film. On the other hand, active remote sensing uses its own light source. Put a flash on the camera, and you've made it active because the light from the flash reflects off the distant object being photographed. Using active remote sensing, you can take pictures whenever you want because you don't have to depend on the sun to give you light.
Explain how scientists use LIDAR to help them measure the aerosols in the atmosphere.
Here in our lab at NASA Langley, we use a technique called active remote sensing. Now that means that we carry our own light source. We don't wait around for the sun to shine on the object. And we use short pulses of laser light to probe the atmosphere. This technique is called Lidar. Lidar stands for light detection and ranging. A Lidar uses short pulses of laser light to detect aerosols in the atmosphere. NASA Langley is involved in active remote sensing from the ground and in the air. At NASA Ames in California, Lidar is flown in the high-altitude ER-2 aircraft to record atmospheric data. And at NASA Dryden, also in California, a high-altitude solar-powered, unpiloted airplane is being developed that can stay aloft for weeks, even months, at a time to make atmospheric measurements.
So how does LIDAR work?
Well, first of all, we open this trap door and then align our LIDAR under the open sky. Then we shoot a pulsed laser beam into the atmosphere. Some of that laser beam scatters off the tiny aerosol particles and scatters light into this telescope. The light is then captured by this detector. By precisely timing the laser pulse going out into the atmosphere and the reflected light coming back to the telescope, scientists can accurately measure the location and number of aerosols. Now remember, this is active remote sensing, much like that flash on the camera.
Okay, I understand passive and active remote sensing and how LIDAR works, but how do you measure the distance from the ground to the aerosols in the atmosphere? You can't use a meter stick.
Okay, let's say you wanted to measure something far away, say like aerosols in the sky. You're right, you wouldn't use a meter stick. Scientists at NASA Langley use mathematics. A pulse of laser light is shot from point A. The beam travels from point A to the aerosols at point B. Then the light reflects off the aerosols and bounces back to point A. If you know how fast it takes for a pulse of laser light to travel, and you know a little math, then you can calculate how far away the aerosols are in the atmosphere. Check it out. It takes a pulse of light 1 nanosecond to travel 1/3 of a meter.
What is a nanosecond?
A nanosecond is 1/1000th of a second. Basically, it's a really small amount of time. Anyway, if a scientist shoots a pulse of laser light at the sky, and that beam reflects back, say in 6,000 nanoseconds, the aerosols in the sky are really 3,000 nanoseconds away. Why? Because you have to divide the total time by 2 in order to find the time one way. Got it? So, if you multiply the time one way, 3,000 nanoseconds, by the number of meters in a nanosecond, 1/3, you get 1,000 meters. If you know how to convert meters to kilometers, you can calculate that the aerosols in the sky are 1 kilometer away.
Well, that should answer your question, Van. But you know, in order to get the whole picture, we need to measure aerosols from space. Let me call a few colleagues of mine over at Hampton University who are working with NASA Langley Ball Aerospace and the French Space Agency to get them to explain to you how we can measure aerosols from space.
Well, while Dr. DeYoung makes those arrangements, let's travel to the Wind River Reservation in Wyoming, where students at St. Stephen's Indian School are being atmospheric detectives.
Welcome to St. Stephen's Indian School!
St. Stephen's Indian School is a BIA grant school situated on the Wind River Indian Reservation in central Wyoming. The reservation is home to nearly 10,000 Native Americans, mostly of the Northern Arapaho and Shoshone tribes. Students work hard on the usual subjects like math and English. We are very proud to be involved in this project.
Soccer!
NASA Connect asked us to show you how to do the lesson for this show. Here's how you can become real atmospheric detectives.
Once you've gathered the materials listed in the Educator's Guide, locate a specific outside area that is flat, elevated, and open. Divide the class into 4 research groups. Each group then tapes one piece of contact paper to the center of the cardboard. Tape the one piece of contact paper in the center of the cardboard with the sticky side up. Keep the protective backing on the contact paper. Repeat the above procedure for a total of 2 aerosol samplers for each research group. Each group is then assigned an area on the school grounds in which to place its sampler. Each group completes the morning column on Table A, Observations of Weather Conditions, on Student Data Worksheet number 1. You'll need to refer to the local paper, watch the local weather report, or visit www.weather.com before completing your observations. Now place one of the samplers on a flat surface, preferably a meter or 2 above the ground. Remove the protective backing from the contact paper. After exposing the sampler to the outside air for at least 2 hours, place the aerosol sampler grid side down, over the contact paper and return the sampler to the classroom. Using a magnifying glass, or holding the contact paper up to a light, count the number of aerosols found in each of 10 randomly selected squares on the grid. Randomly select the squares by tossing the dice twice. Record the number of aerosols in each sample square on Table B, Aerosol Sampler Collection Data, on Student Data Worksheet number 1. Add up all the aerosols in the 10 randomly selected squares to get a total. Next, divide the total number of aerosols by 10 to get an average or mean of the aerosols per square. Repeat the procedure for the afternoon samples. After the average number of aerosols per square for each of the 2 samplers has been calculated, construct a line graph using the aerosol sampler line graph to compare the data. After you've completed this activity at school, you'll take your own sampler home. Place your sampler on a flat surface 1 to 2 meters above the ground. Leave your sampler outside overnight. First thing in the morning, attach the aerosol sampler grid side down, to the contact paper. Bring your sampler to school with you. When you get to school, your teachers will give you time to randomly select your 10 squares. Find the average and record the data in Table C, Aerosol Sampler Data, Collection from Home, on Student Data Worksheet number 2. Next, you'll write your address and the total number of aerosols from Table C on a self-adhesive note. Your teacher will divide a map of your community into 4 regions: Northeast, Northwest, Southeast, and Southwest. All students will place their labeled adhesive notes onto the map where they live. Using the data from the map, find the average for each region and make a class graph of the data.
Analyze your data, guys. Now that you have the results from your sampler, you should review the data and discuss your observations. Then, consider these questions. How can weather conditions affect the results of this activity? What are some other methods you could use to collect data on aerosols in the atmosphere? Look at your map of your community and the data collected from home. What is the relationship between where students live and the amount of aerosols collected? Teachers, check out our NASA Connect website. From here, you can download the Educator's Guide, where you'll find more questions like these that'll help your students analyze their data. Now, let's head back to Hampton University and meet Dr. John Anderson. Dr. Anderson uses space-based passive remote sensing to measure aerosols in the atmosphere. Remember, this type of remote sensing is different from Lidar, which uses active remote sensing to measure aerosols. Dr. Anderson's passive remote sensing system is actually above us right now. on a satellite in space. A satellite is any object that orbits another object in space.
Compare and contrast Sage 2 with Picasso-Cena.
How will Picasso-Cena help scientists measure aerosols more accurately?
Dr. Anderson?
Hi, Jennifer. Hi, Van.
Hi.
Dr. DeYoung told me you guys were coming over to learn how a satellite instrument measures aerosols.
Yeah, actually, he thought you could help us out on information about the satellite system you use.
I'd be glad to help. I'm involved with a satellite instrument called SAGE-2, which stands for Stratospheric Aerosol and Gas Experiment. The less sunlight that gets through the atmosphere at specific wavelengths, the higher density of aerosols there are in the atmosphere. A way to demonstrate what the SAGE-2 photometer might see up in space is to hit two erasers together and shine a light through the dust. This light from the flashlight represents the light from the sun. Researchers look at the reduction of the sun's light to measure how many aerosols there are between the sun and the satellite. Remember, SAGE-2 only uses light from the sun. You know, Van, when I was a student in college, I had to actually collect samples from a real cloud.
Really?
Oh yeah. I would climb Mount Mitchell, North Carolina when the clouds would collect around the mountain. Droplets would form on a Teflon string collector I would hold up and would run down into a container. It demonstrates the same principle which applies when water vapor is attracted to an aerosol in the atmosphere to create drops in clouds.
Cool.
Say, how would you like to learn about the Picasso-Cena system?
Okay.
Picasso-Cena, like SAGE-2, will be a satellite-borne instrument that measures aerosols. But it is quite different than SAGE-2 in that Picasso-Cena uses active remote sensing, while SAGE-2 uses passive remote sensing. My colleague, Dr. Ali Omar, is developing the Picasso-Cena system along with Hampton University, NASA Langley Research Center, Ball Aerospace, and the French Space Agency, CNES. Why don't I send both of you over to see him right now?
That would be great. While Van and I head over to meet Dr. Omar, why don't you meet Dr. Shelley Canwright? She's got a special NASA connection to the web just for you.
NASA Earth Science researchers routinely use technology in conducting experiments and analyzing and communicating the results. Matter of fact, these researchers are much like a detective, collecting evidence and investigating a range of suspects that might be contributing to the situation. I'd like to introduce everyone to a class of online atmospheric detectives at East Palo Alto Charter School in East Palo Alto, California. They've taken on a case that Langley's Learning Technologies Project has posted on the NASA Connect website. Let's check in on them.
We've been asked by NASA to investigate two puzzling situations related to remote sensing. After doing a background check on remote sensing and checking out the application of remote sensing by bats and satellites, we felt prepared for the NASA Connect Web Challenge. In the first puzzle, Satellite Site, we have been challenged to identify facts about the mystery image that you see on your screen. The questions, where, what, and why, help guide us through an interpretation of the image. Hey, now I can name each geographical feature in the satellite's image based on its color. You can do it too. Just visit Norman's lab on the NASA Connect website and find the Atmospheric Detectives online activity button. The completion of the first puzzle prepared us for the detailed attention we would have to give to figure out the second half of the remote sensing puzzle. In the next activity, atmospheric aerosols, we're trying to figure out the density or concentration of aerosols over two different regions of the Earth. We're using information such as relative density, altitude, distance, and latitude and longitude to interpret data about the image just like scientists do.
Well, Jennifer, it sounds like the case being worked by the East Palo Alto Charter School students could use some more sleuths. I would encourage our viewers to visit the NASA Connect website to take a crack at these remote sensing puzzles.
Thanks a lot, Shelley. Hey, while you guys got connected to the web, Van and I met up with Dr. Ali Omar. He's a scientist who studies the atmosphere using satellites. And hopefully he'll be able to convince Van of the importance of keeping his car emissions low.
Thanks, Jennifer. First of all, let me welcome you to Hampton University's Computer Lab, where some of our students are studying atmospheric science.
So, Dr. Omar, how does Picasso-Cena measure aerosols in the atmosphere?
Well, Van, of all the aerosol measuring systems you have seen, Lidar, SAGE-2, and the aerosol sampler used by students at St. Stephen's School have their uses, but they also have their limitations. Picasso-Cena is being developed for launch in 2003 to give us a more complete picture of our atmosphere. The Picasso-Cena mission will greatly improve our understanding of the nature and magnitude of radiative effects of aerosols and clouds. There are many uncertainties as to whether a cloud heats or cools the Earth's surface. This is due to inadequate knowledge of how cloud layers are distributed within the atmosphere. Picasso-Cena will help us obtain more complete observations of cloud distributions and properties. Picasso-Cena will also use Lidar in combination with an instrument called a spectrometer. The spectrometer is a passive remote sensing instrument that measures the radiance of scattered sunlight. Using both Lidar and spectrometer observations will provide us with a more accurate measure of aerosol and cloud properties than either technique alone. Changes in climate are inevitable, but the rapid pace of change that may be starting to take place presents a potential threat to our planet. The new knowledge from Picasso-Cena will improve our ability to make accurate predictions about these changes. Predictions to help world leaders define policies that affect us all. So you see, Van, a little bit of emissions from your car combined with all the other emissions affect us all. We know the world's population is growing, and there are certain things we need to do now in order to protect our environment. One of those things is getting your catalytic converter fixed.
Okay. Well, thank you very much, Dr. Omar, for all your help.
Thanks a lot, Dr. Omar.
You're welcome.
Appreciate it. Well, we'd like to thank everyone who helped out with today's show, especially all the students who were in the program, the NASA researchers, Hampton University, and of course, Dr. Shelley Canright. If you would like a videotaped copy of this NASA Connect show and the Educator's Guide lesson plans, contact CORE, the NASA Central Operation of Resources for Educators. All this information and more is located on the NASA Connect website. So, for Van and the rest of the NASA Connect crew, I'm Jennifer Pulley. So Van, what are you gonna do?
You know, Mr. Murphy, it's important to have your car running right and clean. Not only is it healthy for breathing, but it's also good for the environment. Hey, is that your car out there? Kind of a clunker, wouldn't you say? Huh? You ought to get that inspected. And fixed. And cleaned. Did you know that the atmosphere contains aerosols? An aerosol is a particle suspended in the air, and aerosols help to form clouds. Some clouds bring rain, but some clouds trap the sun's rays, bringing global warming. But all clouds reflect the light, which can cause global cooling. It all has to do with particles becoming aerosols. Say, you know there might be particles coming off this tailpipe right now. See? More soot into the atmosphere. We ought to fix this. Maybe I can move. Oops. Sorry, Mr. Murphy. Maybe you should clean up.